Hello, everybody. We're going to do section 6 today. We're going to talk about something called continuous mapping and MLE consistency. These notes are, this section of notes is to dig more into this idea about when maximum likelihood estimators are consistent and when they're not, because maximum likelihood estimators are such a useful tool. They are the value of the parameter that maximizes our objective function, which is the likelihood maximum likelihood estimators. Continuous mapping is a helpful little tool that will allow us to prove things. We're not going to worry too much about the proof, but we are going to use the tool here and there. And that's what happens if I take a function of a maximum likelihood estimator. I'm going to learn that we converge essentially to the function of the truth. And we're going to go through there and with some helpful examples. So let's get started here. So I guess the best place I think to start here, and I'll make this a little bit bigger so we can focus, is we know that the sample variance converges to the true variance, right? We know that the expected value of s squared is equal to sigma squared. And we know that s squared converges to sigma squared, to the true variance, as the sample size grows. Well, then, if the sample variance converges to the population variance, what happens to the standard deviation? Is it true? Then, well, that the sample standard deviation, this thing right here, converges to the population standard deviation? Really? And in fact, it's going to turn out to be yes. And it's going to be very simple, turns out, to make these sorts of statements and claims. And that is, what I'm asking is, if I have some function of an estimator of the sample variance, h of the sample variance here, I'm right here, does this converge to the function of the truth? Because what you have here, and this should seem like it's pretty natural. So this thing is converging to this thing. So does this whole thing converge to this whole thing? Right? Essentially, we're taking the square root. So does the square root of s squared converge to the square root of sigma squared? And that would imply that s converges to sigma. And here I have just Sn, so we know it's the sample variance depending on n. The answer is that while the law of large numbers won't give us that, we know that this is true from the law of large numbers, right? That the sample averages converge to their population mean. We need a slightly more, we need to be slightly restrictive about what functions we use. But if we use well-behaving functions, smooth functions, functions without big jumps, then in fact, these sorts of statements just come naturally. We can use what's called the continuous mapping theorem. The continuous mapping theorem is super helpful. It says, look, suppose I have a sequence, and this represents our estimator, and I have some sample space, and let G be a function from one place to the other, and there's a set of discontinuity points G. Then if you don't end up at the discontinuity, then this thing will converge to what you think it will be. That means if you know that xn is converging to x, then g of xn will converge to g of x as long as there's not a discontinuity. The way to think about this is the following. Let's suppose I have some function x, and then let's suppose I have some function g, and g, let's take, for just to begin with, let's take a nice smooth function. This is g of x. This is g of x. I don't know what that was. Hey, that was a mistype there. Let's see. Here we go. Typo. Yeah, it's a typo. So that's g of x. Now, what does it mean? What does this statement right here mean? And in fact, let's back up. Let's just take a simple convergence and probability. Xn's are converging to x. Well, Xn's are your estimates. So I might do a sample And I might say, oh, hey, I'm going to look at, let's say, the sample mean based on 10 observations. Then I might look at the sample mean based on 12 observations. Then I might look at it based on 20 observations, blah, 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 blah. And I get a bunch of samples, and they eventually converge to some place right around here. Let's say they converge right to here, and this is going to be mu. And we know, of course, that the sample averages are going to converge to mu as n goes to infinity. So on this axis, basically you have a bunch of dots. They're jumping around, they're converging. And so what happens then in the function space is almost the same thing. You get some jumping around on the function space here, and you end up at this place. Well, what is that place? That, it turns out, is g of mu. So if the x's are converging to mu, well then surely, let me rewrite this here. Then, whoops, hold on. Let's get rid of that. Then surely, then we should have a similar thing. So if I have x bar converging to mu, then it turns out that g of x bar will converge to g of mu, because everything that happens nice down here in this space happens on the line. And so the convergence that you actually get, even though it looks like it's happening on the curve, the convergence is actually happening here. This is g of x10. This is g of x bar 20. This is g of x bar 12. And this red line here is g of mu. So this, if you could see the dots right down here, this convergence and this convergence are related. So converging to the red on the x-axis converges to the same point on the y-axis, just in the functional space. And that's all because this nice black function is nice and neat and smooth. Now, this will break, and this can break if your function's not nice, neat, and smooth. So if, in fact, I were to take a case where, well, hold on, let's see. Let's see if I have a little space. So if I were to take a case here, hold on, let me do this better. If I were to take a case here, here's x, and let's say my function goes like this. Now this is g of x, so I got a big break in my function. And the break here occurs at some discontinuity d. And I have a bunch of convergence here going on here. The x's are converging. X's here are converging. X's are going to some x, right? Or x bar going to mu, something here. Then I'm going to see similar convergence space on this line. So I'll get convergence here. So this is just the case we did. So I converge to the red here. I'll converge to the red on the y-axis. That's fine. And the same thing happens on the other side of the discontinuity over here. The problem that happens is when you're converging right around to the discontinuity, and see these purple is discontinuity here, the observations that are on this side will all be down here. The observations that are on this side are all going to be up here. And so what happens is that you get a big disparity. So in this case, if your x's are converging for d, it's not true that this thing converges always to g of mu or g of d, because you could be coming from the right, could be coming from the left, and you could end up either here on this top part, you could end up on the bottom part, depending on which side you happen to be approaching from. And so this is a problem. And so basically, as long as the function that you're using is nice and smooth, we're all good to go. You can just go on and apply functions all over the place. unlike expectations, you can do this with limits. And so the square root function here works very nicely. All right, so then let's take a look at how we might use this. We're not going to prove this. We don't care. Let's see, some notes here is, this is my shorthand for the sequence. The function only needs to avoid a discontinuity in the limit, right? So that means you just need to end up at a point in the function that's not discontinuous. That means if you come down the function, you come up the function, you end up in the same spot. This is called the Man-Wald theorem. And so back to the variance example, if we apply the continuous mapping theorem, we get this because the square root is nice and smooth. Okay. The hard part is to understand here, let's connect back, is that it turns out that Sn is a biased estimator of sigma. That is, the expected value of Sn is the expected value of h of Sn, where h of x is equal to that square root function here, right? This is for Jensen's inequality, right? Jensen's inequality. So that's going to be less than this thing. Okay, here I pulled the h out. This thing is sigma squared on the inside here, which is sigma. So I have, and what I've shown here, and let's use a different color, is that the expected value of Sn is less than sigma. But we know that Sn converges to sigma because Sn squared converges to sigma squared. And because of continuous mapping, I can do the square, I can put the square root on both parts. So we have a very interesting case, which is that we have a biased estimator that is consistent. That means on average, the estimator is not equal to the thing we're interested in, but in the limit, the estimator will end up at the correct place. Well, what is that? So this turns out to happen a lot. So this is important. And the way you can imagine this happening is that the bias that you're getting shrinks a little bit. Do you remember, if you remember for the maximum likelihood estimator for sigma squared in the normal model was this guy over n, and the expected value of sigma hat squared was 1 minus 1 over n sigma squared. So there is some bias, and that's the 1 over n, but the bias goes to 0 as n goes to infinity. So this thing is consistent. So we end up at the right place, even though there's a little bias. So this is one way that we handle problems with Jensen's inequality or Jensen's inequality, is we use the continuous mapping to show up that we end up in the right place, and then we notice that we have some bias, and then that bias has to go converge to 0. Bias shrinks with the sample size. So here I'm going to do a couple of examples. I think it's helpful to sort of think about that. Suppose I have something that converges to x and something that converges to y. Well, then the ratio of x over y should converge to the correct thing. So this is true. But we know that the expected value of this is not equal to the expected value of each of these things, right? Which would be equal to x over y in this case. So we have a not equals to. So in fact, we have that the expected value is equal to the thing plus a little bit, but that little bit, that bias is going to 0. And this happens a lot, in fact, with maximum likelihood estimators. Maximum likelihood estimators, we just showed with the maximum likelihood consistency, maximum likelihood estimators tend to go to the true thing that they're estimating. But very often, they'll be biased. Well, how do you end up at the right place? You end up at the right place by being equal to the truth plus a little extra. But the extra is going to 0. It's disappearing as the sample size gets big. Does that make sense? It's a little bit like saying you're always going to be off by a fraction of the sample size. Let's say I'm going to be off by 3 observations of the sample size. Well, when I have 6 observations, I'm off by 50%. When I have 100 observations, I'm off by 3%. When I have 1,000 observations, I'm off by 1/3%, et cetera, et cetera, et cetera. All right, this is a really cool example of an inconsistent maximum likelihood estimator that we are going to completely ignore. If you want to take a look at it, I'd be happy to go through you. It's a little bit weird. It's old school. I've used it in some stat cases. I don't know that people get it very much. I have some pretty graphs. Look at that. That's pretty. Okay, we don't care. All right. So here's the case that I want to pay attention to. And that's what happens when you have an inconsistent maximum likelihood estimator. And this is a really good and important example because Neyman and Scott were one of the first people to estimate what happens when you're trying to estimate a particular parameter, but when you have more extra parameters than you have data points. So what's the situation? They said, okay, suppose I'm going to collect pairs of observations on people. So here is, but the pairs are independent. So people are independent. So suppose I collected foot size. How big is your left foot? So this is left foot size and right foot size. That's what I'm going to take a look at. So those things are obviously related, but I'm going to do it for lots of different people. And in fact, the distribution of feet size, they said, suppose it's normal. And in fact, that everyone has their own foot size, and that's mu I. But the variance is the same. So the variance in foot size is the same over the whole population. But of course, everyone's got a different foot size. So that means every time I take a pair of observations here, I'm going to end up with a normal model that's mean 1 sigma squared. So then when I take my second pair of observations, those come from a normal mean 2 sigma squared, and et cetera come from a normal mean n sigma squared. So if you look at and you add up the number of parameters here, you've got a sigma squared, and then you've got a mu1 all the way to a mu n. You've got a whole vector of parameters. So you've got n plus 1 parameters, but only n observations. So something's going to go wrong. That's what makes this case so interesting. So let's just take this case and let's find the maximum likelihood estimator of sigma squared. Now, since these are jointly normal, you can write the joint normal distribution as this piece here. And then you're going to take the multiplication, right? Because the likelihood over all the pairs, these are the pairs here. And you get this particular formula. And this, it looks like this, because all I did was move the product through the exponential up top here. And then what I want to do is I want to maximize the likelihood function, right? Don't forget, mu here is this vector, is that vector right here. So I want to maximize this likelihood function as a function of sigma squared. I don't know what the mu's are, but I'm going to maximize them. And so it turns out that the derivative of the log likelihood with respect to sigma squared is equal to this thing. And so all I'm going to do is set that thing equal to 0 here. And what that means is I get a maximum likelihood estimator that looks like this. And this should look pretty familiar here, right? I mean, this is basically the sum from I equals 1 to n, right? And then there's a 1 over n out front. And then there is a sum from j equals 1 to 2 that's inside the pair, xij minus x bar I squared over 2. So basically what I'm doing is this is the variance for the pair, and then I'm taking the average. over all pairs. Basically what I'm doing. Except we're going to have a problem, right? Well, what is do you remember what the bias was? So the bias for sigma hat squared was 1 minus 1 over n sigma squared. Oh, well, that was its expectation. The bias was 1 over n. So in this case, it's 1/2. And that's what we get. So the expectation of this thing turns out to be sigma squared over 2. Now, wait a second. So this means that our maximum likelihood estimator in this case is converging to half of what the variance is. And the reason this happens is because in each pair, you're computing the variance. You're taking all those estimates of the variance and then you're averaging them. But all those estimates of the variance suck. They stink. They're only based on 2 observations. And it doesn't matter that you average them. You could average them 1,000,000 times. Each of them has a bias of half the variance. So you're just averaging that bias 100,000, 1,000,000 times, however many times. And you end up with still a biased estimate. So if you have a crappy experiment, this is a little bit like saying, okay, well, if I have an experiment with 2 observations, I'm going to estimate the variance. Well, that doesn't make sense. And if you then say to me, well, I'll do it 100 times, that doesn't make sense either. If you try to drive your car through a brick wall, that's not going to make a lot of sense. That doesn't work very well, right? And if you do it 100 times, doesn't make it any better. Same problem here. Same problem here. Okay. And this is what was interesting to Neyman and Pearson. So they calculated, you can calculate the variance of the maximum likelihood estimator, and it's this thing. All right. And I'm not going to worry about how we do that. We get all sorts of random variables. But now these 2 results will imply that the MLE is not consistent for sigma squared. This is just what we were talking about on the last page. And we can talk about, if you're curious about how you prove consistency in particular sections, we could talk about how we do that. So the bias here does not go to 0. And the bias doesn't go to 0 because the number of observations in each pair is not growing. Each pair has some experimental bias. Averaging those a whole bunch of times doesn't help. It leaves the bias there. Now, we're going to come back and take a look at this in 1 second. In the next section, we're going to look at this in detail, and we're going to see what happens when I increase the number of observations within each pair. Things go away. But this is not unusual for problems in which you have more parameters than you have data. You get biased maximum likelihood estimates. And what are maximum likelihood estimates? Maximum likelihood estimates are just solutions to an objective function. So when you have more parameters than you have data, you have to be very careful about interpreting and understanding what those parameters are. You have to make extra cases. You have to make your case for why something is interpretable or not, because most of the time, things break down and don't work. In this case, it's possible to resolve the problem. So Neyman and Pearson noted, they said, hey, the trick is that you take each observation in the pair, take the first observation, and subtract the second. Now this has a normal distribution, mean 0 and variance sigma squared. And now you can go estimate. Now you can go estimate this thing. Actually, you need 1 over the square root of 2 here. You need a little 1 over square root to get the right variance. Otherwise, this is twice the variance. And now, if you take the squared differences, this is the usual unbiased and consistent estimator of sigma squared. The price here that we pay is we can't learn about all the means. And we can't learn about the means because there's very little information. There's only 2 observations for each mean. So if we don't try to learn about them, we can learn about the variance. So what this example teaches us is that how we set up the working model is very, very important. You want to set up the working model in a way that you can estimate the parameters. Unknown parameters that are not necessarily of interest may affect the estimation of the parameters we're interested in. So if you have a model and you've got a bazillion parameters, you say, I'm only interested in the first one. You have to be careful because trying to figure out what those other ones are may indeed affect what you're trying to do to estimate that one particular observation. All right, there are some general consistency conditions here, and I'm just going to read these off. These are things that you can look up and you can remember. When you have a highly discontinuous likelihood function, you have weird things. And when you have an infinite number of nuisance parameters, you have weird things. So these are the two cases where the maximum likelihood estimates are weird. And so in general, for consistency of the maximum likelihood estimators, you need something called identifiability, which we talked about. And you need compactness of the parameter space. What's that? That means you need to not have likelihood functions that look like this. Here, notice I'm approaching the maximum at two places, the truth and another place out here. And so when I go to maximize this likelihood function numerically, you don't want to get stuck over here because this is in the wrong place. So we rule out these sorts of cases. When we have these, I may not get the right answer. All right, and in continuity, you want smoothness and the existence of derivatives in this function. And there's a mathematical boundary here that's helpful that we don't have to worry about at the moment. I think I just say what all these things put together here. Okay, it's good for now. In the next one, we're going to talk about the Neyman-Scott problem and we're going to get back in detail to that particular problem that we just looked at.